tell you before is that, remember, for this guy, why this one should be diode connected, that will make this guy unconditionally in the saturation region. So you can have it at the flat level, because that will give it, then you may make use of this guy to bias it, because let's look at the equation of ID is equal to, usually use Kn, right? Now I break the Kn into two parts, Kn part and the W over L, right? So divide by 2. Previously this whole thing is Kn, right? So then VGS minus VGN for M moles squared. Okay? And because we want to take care of, if this is the case, then your ID characteristic will be flat, but actually there's a bit of slope. So to take care of that, we have this channel modulation case that depends on VDS. So this is a complete equation. And then, as I mentioned before, in amplifier, small signal amplifier, we can ignore this part because now this is small. And here is still small, it's the same thing. The only part is now even very small, we want to see the difference, because the slope is not an ideal case now. I want to look at the practical current mirror. If I look at ideal, I take it as flat. Okay, now practical current mirror, then we cannot ignore this, otherwise it looks like an ideal once you bias in the saturation region. So, having said that, now you can see for yourself. I'm going to draw this out here. VDD I reference. Then you have this guy here, here. Then you have one branch, and this is 10 volt. Then another branch. This is 8 volt, and then another branch. This is 12 volt. So what the difference is the VDS, VDS is GSD, right? Okay. So I think you can easily see that. I want to show you one thing. Here we label the 4/1 is the W over L ratio, this guy. So for this transistor, the 4/1. So W is 10, L is 1. That's the ratio. Width to length is the ratio of this guy. This the width to length of the channel is 40/1. Okay? So let me do a case where you notice VGS gate source of this transistor, same as this one, right? Your gate connect to gate. This punch through is not that you go through, it's just that we don't want to draw complicated thing, so you just take this point directly connect to here. Okay, you cannot go through the transistor like that. Okay, so then gate to gate, gate to gate, gate to gate, source all connect together, right? So all these have the same VGS. So you can see all of them is the same, right? And then according to the question, all of them also have the same VGM, right? Alright? So what they are different is VDS, right? Yeah? So let me take the most ideal case first, then you do an estimation of what is the current you can get. So if I take the most ideal case, this guy is not here there, I assume 1 guy equals 0 first, ideal case. If this is 0, this term is not there, 1 plus 0 is 0. So in only this term, you can see that Km is the same, right? So the current for each of these, the drain current, this guy here, ID, this guy here, ID2, ID3, ID4. Yeah, different is basically W over L ratio, right? Agree with me? So if you take ID2 over ID1, what do you get? W over L, 2 over W over L1, right? Okay? Because the rest of the term is the same. So if you take copy, then you cancel out left with W over L. So if that's the case, based on this most ideal case, you can see this guy is 10 times over this, right? So that means this will be 2.5 times this current, right? So what is this current? There's no gate current going here, right? Since this no gate current, all these MOSFET, right? No gate current current means there's no current here. Current here is 0. That means then this is equal to this, right? So if I know I reference, I know ID1 equal I reference, right? So what is the I reference given to you? 30 micro, right? So that means ID2 will then be 10 over 4 times 30, right? So it's 2.5 times 30, how much is that? 75 microampere. If lambda equals 0, huh? So ideally you can also get this guy what I said, huh? This is compared with this is about 5 times, right? So that means ID3 will be 5 times I reference, huh? And that will give me 30 times 5, 150 micro, right? So how about this guy? ID4 will be 10 times, right? So it will be 10 I reference. Then this guy will be 10 times will be 300 micro. This is when I think lambda equals 0, huh? But when lambda is not equal to 0, you can see because each of them have a different VDS. Then you affect this current from this one. So ideally you want it to copy with this ratio determined by the W over L. But in actual fact you will deviate on this ratio. So the deviation from this ratio we call it mirror ratio. Got it? Okay? So in this case for this one, but the mirror ratio is just W over L ratio. Huh? But then when you take this into consideration, the W over L ratio is more than it's changed different from W over L ratio. That is called the mirror ratio. Mirror ratio means the branch current here and the branch current here as a ratio. Okay? So I think it's easy to understand by if you look into a mirror, your mirror makes you 2 times larger than the mirror ratio is 2 times. Okay? But here, if you only depend on this, is assuming lambda equals 0. So let's look at the question here. What are the output current and the output resistance? We'll do the output resistance calculation later. We just get the output current first, which is the DC drain current. So if lambda is equal not 0, but 0.015. Here I purposely use 0 to show you the concept first. So when it's not 0, let's see how we do the calculation. I'm going to show you the solution directly and then explain from there. Okay? So now, first of all, I will refer back to this diagram. One thing you notice, this for the first transistor, the drain source voltage is the same as the VGS, right? Alright? So am I able to calculate the VGS if I know I reference? If I know I reference means I know ID1, right? Because I circuit current. So that means my ID1 is equal to I reference equal to 30 microamp. So now if I want to take the actual case, this is the general equation for all the transistor ID, right? So if I take this one, put in ID1, then I have 30 micro on the left hand side. Then Km time, the question given to you, right? How much is that? 35 micro. Okay, then W over L for this guy is 4 into 1, so it's 4. Okay, then 2 here. Then you have VGS, which is you don't know, you have to calculate for the first transistor, VGS on. Then minus VGS given to you is 1, is it? 0.75 square. Theoretically, okay, you should also put 1 plus lambda VGS, but the VGS is equal to VGS. So then you have an equation that is quite difficult to calculate. Okay, actually, in the extra slide somewhere, okay, I have this equation, I actually solve this, okay, and then show you that the difference is actually very small. So for if you are not looking at the mirror, you're only interested in calculating VGS for the first case. If you don't want, then you can see 1 plus, what is it? 0. What is lambda? 0.015, right? Then you have to put your VGS 1, because VDS is equal to VGS for this guy. So then you can see you have an equation that involves power tree of VGS. So then you solve it, you have 3 solutions. I can't remember the earlier I created some slide. Last semester I didn't teach, so I can't remember where I placed the slide. If I want to search, I can find it. Okay? Let's see this first. Okay? So if I ignore this part, then you can see my VGS, if I put it up, okay, rearrange it, actually get this equation basically. 2ID over Km, Km is Km prime W over L. So it's same as this guy. So if you rearrange, substitute all this in, you can work out your VGS is equal to 1.52. Okay? Yeah. So once you got this, the next part, what do we do? Then I take this ratio over this ratio. Now I want to take into account this guy. So what I need to do is I substitute ID2, this becomes ID2, right? Then this is the same, but W over L is different, so this is W over L2. Then this is VGS2, But VGS2 and VGS1 is the same because they all have the same VGS. I can put them as VGS all. Okay, which I already calculated, basically. So then this guy given VDS. For this guy I know, For this guy is 10, D to S. For this guy is what I calculated here. 1.52. That's the reason why I need to calculate this. So now you can see I'm substituting basically the equation, same chain equation here, but for ID2. This one is for ID1, the first branch. Can you see that? So then these two, because VGS all of them are the same, so this one cancel out. Okay? And then Kn is the same, this one cancel out. So you're left with this ratio. Okay, so this ratio, if you substitute in all the known value, but this VDS for the first transistor, this guy should be VDS, but for this one, your diode connected is equal to VGS, which we calculated here. So now because of this, I am able to calculate this ratio, and I also know ID1, because ID1, there's no gate current, ID1 is equal to Ireference, Ireference is given to you. Alright, so the moment I know this ratio, can I calculate ID2? Just take this ratio multiplied by Ireference, Your Ireference equal ID1 equal Ireference. So because of that, I can look up ID2 is 84.3 micro. So let's compare with the one I ignore this guy, right? Just now I calculated 75 micro. So there is a slight difference, this current. Can you see that? And that difference is because this guy is different from this. And there's quite a lot of different. This 10 volt, this only 1.52. But the current difference not as bad. Okay? So that's why it is good, still a good constant current source. So let's look at the I will skip this, maybe I don't need to skip it. Once you can calculate the drain current, then you will be able to find the resistance of the current source. Remember every time we talk about resistance of current source, previously when we do differential amplifier, we say it is the AC resistance, right? So if you try to look at this transistor, what is AC resistance? If you replace this by the small signal equivalent circuit, you see that here drain, here source. Between drain and source, you see the RO, right? Value. So there's no other thing. You replace this by small signal equivalent circuit, basically see RO at the output from this terminal to ground. So the small RO is given by this equation, which is given to you in the formula sheet during exam. So it's 1 over lambda plus VDS divided by DCID. So VDS is 10 volt. DCID, that's how you calculated 84.3. So you substitute inside, you'll get the resistance. So you can see that for current source, okay, do you want to take this guy as the current source parameter? The good current source means that this DC current doesn't change a lot with this voltage across it, across the terminal here. So that means if you look at it in terms of the IV characteristic, totally don't change with the VD across is 10, but this guy is not, so you have some like that. So like that means there's a slope, right? This is your AC resistance from here to here, and in this case for this configuration is up. So it should be big. The bigger it is, the better you are. That means the variation of the this voltage doesn't affect this current that much. Okay? So this line quite big, but later you can see we can make this resistance across the terminal even bigger in other configurations. That's the difference. Okay? Now if you can do ID2, okay, by taking the mirror ratio of these two, right? Can you calculate ID3 in the same way? I can take the mirror ratio of this and this, right? The mirror ratio of this and this is basically equal to this with this term, 1 plus lambda b ds2 over 1 plus lambda b ds1, but b ds1 is equal to bgs, right? So we already calculated this guy is 1.52. So basically we get the ratio. Okay, then I know this guy is equal to I reference. So I can work out ID2, just now that's what I do. So can I change this to try to find out ID3? Just by changing this guy to 3, right? Then this guy to 3, right? And this guy to 3, right? The same way I can calculate this ratio. Then the same way I can work out the current. So this is precisely what we do. As you can see, the bottom is still the same, huh? Because I didn't change the ratio against ID, this guy. Huh? This guy remains here, 4. Is 1 plus lambda 0.15 times 1.52, right? And on top is, now I have to use this guy. This guy, the W over ratio is 20, right? So it's C20. Okay, 1 plus lambda is 0.015, and then BDS here is 8 volts. So I get this ratio. Okay, then I shift the ID1, which is I reference, over. Now I can calculate ID3, right? So ID3 this time, you see it's 164 microampere. Huh? Okay, but you compare with this ID1 without lambda effect, if lambda is equal to 0, you can see it's 150, right? So the deviation is because there's a difference between this and this, 8 volt and 1.52 volt, right? Yeah. So now the output resistance, you can check for yourself. The output resistance is 1 over lambda plus VDS of this guy. In this case, 8 volt divided by the drain current you calculated. Okay, so you get 455 kilo ohm. You can see this output resistance is not as good as this one, right? So as a result, you can see the deviation actually this guy. The percentage deviation will also be different. Even although this guy, the voltage at the output is smaller, huh? Okay, than the other one. So let's look at the ID4. Okay, ID4 the same way. I did this over this to get this ratio. Then I just change this guy to 4, right? Bottom is the same. So the calculation remains more or less the same. I just every time take 1 pen, reference to this guy, get the ratio, then I calculate. So you can see that the last case here, the bottom is still the same. WL for this reference one is 4, 1 plus 0.015, and BDS just now I calculate is equal, this guy is equal to BGS, we calculate 0.15, right? Earlier. It's a 1.52, huh? Okay, so then for this guy, the numerator W over L is 40, 1 plus lambda, BDS is 12, so you can see this is 12. So I take I1, which is I reference, 30 shifting over the other side. I can work out the current 360 46. Compared with this now is bigger percentage different, huh? Can you see that? This is ideal case where lambda equals 0. Lambda equals 0 means it is independent of what is ever voltage here. That means your R out is assumed to be infinity. Correct? Then it's a flat one. Okay, so it's all correlated. So let's look at, since this is not ideal, then you must have a not infinite resist output AC resistance, but finite. How to calculate that? Is exactly, if you look into here to here, you replace it by small signal model, you can see your small R out. Exactly. Okay, and then R out can be calculated by this 1 over lambda plus VDS. In this case, your VDS is 12 over the drain current ID. So you can work it out to be 227 kilo ohm. So you can see this one compared with the first, this current mirror, the R out is actually case the deviation in terms of percentage is bigger than the ideal one because the slope is poorer. Huh? Got it? That means the sensitivity with the terminal voltage. If you understand what you want as a constant current source, you understand why we are interested in the AC resistance calculation. Okay? Good? Okay, so we are clear with this first question. Can I take this away? Okay? So then we can now move to the second question. First question just now, let me see if I can pull out the, if I can find anything let me see if I have the solution. This is the old one, which has more question.
Using camera to take video of this. Secret. Yeah, they put yourself. Do the for now. Almost done already. Why weekend can do it? We'll find in April. Weekend do it. It's not easy. This week is not easy.
If I can find in next tutorial, I'll make it easier.
Okay, thanks for your test. Just for me. I mean, for me, I don't study. I don't study. I never study this.
Let's come back to the
Unless
next
you
part.
want to just study for partial.
Let's look at this one. Second one, now we are going to do this one is a bit more complicated. Huh? The reason why it's more complicated, the structure, if you can look at this again, it's the same, right? These two structures. Except that the MOSFET changed by BJT. Okay, and also, even I put the voltage exactly the same. Huh? So, I'm going to draw this and show you what has happened. This VCC here, this is I reference. This is a simple current mirror, as you can see. You just simply mirror the two. So this guy is 10 volt, this is ground. Then again, there's another constant current source mirror from here. This is 8 volt. Another mirror from here. This is 12 volt. So this guy is Q1, Q2, Q3, Q4. So this one, A means emitter area, not ampere. Huh? Don't confuse this with the current. This is not 1 ampere, it's emitter area, 1 unit emitter area. So this guy, the emitter area is 2.5 times the emitter area here. Okay? And this guy, the emitter area is 5 times. This guy, the emitter area is 10 times. So you can see this question, as far as if you ignore the early effect, the ratio is actually same as just now the case, right? Can you see that? Okay? So let me put it this way, if you can recall, your collector current, because each of this guy is your IC1, this is your IC2, this is IC3, this is IC4. Okay? So theoretically, this DC current will form the constant current, right? For each of the branch you want to generate the constant current. So I take the general equation for IC versus VBE is base, this is emitter, this is collector. Okay? So IC in general should be IS exponential VBE over VT. VT is thermal voltage. Then this is the one we used to use for amplifier, we approximate. But actually, if this is the case, then if you plot your IC versus VCE, then it doesn't depend on VCE, right? Then every curve becomes to be flat. Correct? But then in actual fact, it's not. It will change a little bit with your VCE. So how do you account for this one? Exactly, it's 1 plus VCE over VA. This is the early voltage. Got it? Okay? So, when we come to constant current source, we have to take care of this term. Okay? So we have no choice because we want to know exactly. Because if you don't take care of this term, it means then ideal. Then RO infinite, VA equal to infinity. Am I right? Okay, if VA equal to infinity, this guy is equal to 1, then it's just the ideal flat case. Doesn't depend on VCE. So in this case, we want to see the effect of the non-ideality, we have to include this term. I want to make this point clear, otherwise every student keep asking why amplifier I ignore now, I cannot ignore. Okay? So the moment you ignore everything ideal. Okay, let's look at how we do it. This one have a small little difference. This IC ones no longer. Just now the MOSFET, there's no gate current, right? So then this equal to this. This one, too bad. This guy have a base current, right? IB1. This guy have a base current IB2, right? This guy IB3, IB4, right? So that means this guy total will be IB1 plus IB2 plus IB3 plus IB4. Am I right? So what is the current IC1? Will now equal to, sorry, how should I put it? That means my I reference, the one that's given to me, will be equal to IC1 plus IB1 plus IB2 plus IB3 plus IB4. Am I right? Okay, the next thing is, the rest by right actually is the same. That means I still do this mirror with this, but based on the emitter ratio. So I forgot to mention one thing. Previously, when now Km, I break it into Km prime and W over L, right? Here I should break this guy. Actually, it depends on the emitter area and the per unit area, what is the IS, saturation current. So in that case, I can break it into A, E, and IS prime. Similar. Okay? Got it? Okay? So I roughly give you this idea. Another thing is each of this I can express, this guy I can express into IC1 as well, right? Because IB theoretically is equal to IC over beta, right? And this beta is beta 1. So here, since we are talking about current mirror, normally the beta given to you during amplifying is the one that is the nominal value, doesn't depend on VCE. So in this case, since I'm interested all in current very carefully, the beta actually will change in VCE as well by this factor. I mean beta, okay, beta of whatever is equal to beta naught. The one that's given to you nominal is beta naught. 1 plus VCE over beta. Over VA. Okay, VA is constant, early voltage. So you also, the beta also increase with your VCE in the similar fraction. So that is the one that makes things slightly complicated. Otherwise, the ratio, we still do the same way as what we do the ratio. And what is the slightly easier part is this. I don't need to, because this guy is DVE, right? So you have to be forward active, right? And since you put diode connected, the moment you can pass the current through conducted, then it will be 0.7, right? So this will be also 0.7 because you connect this point to this point. So this voltage to here and this voltage to here is the same. So your VCE for the first one will be 0.7. Previously, the VDS I had to work out using VTM plus something. This one I don't need to, is 0.7. But the rest of the VCE, this guy is 10, this guy is 8, this guy is 12. Got it? So I clarify this point first, then I'm going to use the slide to show you the working. So let me put it in the key point. Key point. I'm going to use this equation. Then I'm going to take the ratio, this over this, using this equation. And as far as I'm concerned, VBE will be the same, VT is the same temperature. This term will cancel out. The ratio will left with this and this for each of them. Okay. But there is a difference is, now my IC1 is not like the MOSFET case, this is equal to this. No. I had to work out IC1 into I reference, then I have to express this thing out. Each of these I have to convert to this, and this guy is
Where
also
is we? It's not BGT, they have J.
which you will see that in the
BGT is C.
derivation later on. Okay? So I'm going to show you the solution.
BDS.
I explain the key point first. So first, maybe I show it with
Basically, why those two voltage are the same is because of the
make it
wire
slightly
over there. I'm
smaller.
pretty
You
sure
can see a little bit
you
more.
don't know which one
Okay?
it's in.
So what happened here? You can see,
Wow.
as I mentioned, there's IB1, IB2,
Because if
IB3,
you are you won't
IB4.
say the
So
thing
this
I'm not asking.
branching out
No,
the
I
current
don't
here,
say
you have
BGS or VDS.
all these
Some
three current
BGS or
together.
VGS or
Okay? And then you notice that this collector current plus this will be equal to I reference. So this is this equation I put here. Okay? So this is the one that is different from first equation, first one. Then this is a general equation, generalized. You notice the IS I now get into the emitter area and saturation current per unit area. Okay? So this is IS here per unit area. Then this is the area. So this one area, this 2.5 area, this 5 area, this is emitter is 10 times this area A. Huh? So
by default VC is
then I also tell you that the beta of each of the transistor is the beta given to you and it relates to the early voltage and the collector emitter
VCE
voltage across it as well.
Yeah.
So now, what I'm going to show you is that each of these base current I'm going to express in terms of collector current over beta.
So it's like voltage from B
for
to
IB1,
let's say the voltage from C
it will be IC1 over beta 1. So IC1, I can take this guy, substitute everything by 1, and then this beta, this guy is on top, this guy is beta changed to beta, and this guy. So this and this will cancel out for the same transistor. So you're left with this. Can you see that? For the same transistor, the VC should be the same. VA should be the same. So this factor and this factor will cancel out for the same transistor.
Okay,
so IB can then be expressed by this. So that's a good. Clear? So then, if you can do this, then basically the next line I'm actually making use of this equation, which is this guy here, by substituting the first one. This is IC1, first one. IC1, I just put A1 as IS exponential VBE, and this VBE is 0.7, okay, for forward active. So then 1 plus VCE1 over VA. VCE1 is actually 0.7 also, because this guy is diode connected. Okay. So the second term essentially I replaced by IB1, right? IB1 is this one, right? So this becomes A1, okay, for the first transistor. IS, then VBE over VT divided by beta. Beta is the beta given to you. Okay? So IB2, I replace it by A2, IS, VBE, because they all biased by the same VBE. Okay? So divide by beta, and so on and so forth. I just substitute this equation for each of the IB. So once I have that, the common term is this guy, right? I can pull it out. Then I have this expression. Okay, this A is actually the emitter area. For the first one, A1, the emitter area is A. For the second one, the A2, the emitter area is 2.5A. I hope you can see that. Okay? So now I'm going to move to the next part. Is I know I reference here. I reference. So if I take IC2 versus I reference, so IC2, I reference is this expression. IC2, then I need to use this expression. This is 2, then this guy is AE2, IS, okay? Because I have lumped it together. This one is supposed to be ISO. I use the same symbol as him. So VT so on. Okay, this one will change to V1. V2. So IC2, which is the one you want to calculate, this guy, and applying this formula. So I have this A2IS VB2 1 plus this guy, exactly the equation. Saturation current equation. Then This I reference I make it put below. So you can see then this term cancel out, right? So now you substitute the area. This is 2.58. I just put 2.5 because all n have this a. So I substitute the area. This guy is 1a, become just 1. This is just the A1 is 1 or 2. 1, okay? So anyway, just substitute accordingly. A1, A2, A3, A4. So you substitute accordingly, then you should get the result. Okay? I think somewhere this should be mistake. This should be 1, not 2. 1. A1 is 1, huh? Our admitter area 1 is it 1 or 2? 1, huh? Not 2. Okay. So please correct this one. This should be 1. I hope the value is correct. This is anyway supplied by. I think the calculation should be correct, but this one is wrong. Okay. So then this guy is 1. This is 2.5510. The rest is correct. This A1 is wrong. A1 is 1, not 2. Okay. So beta is given to you 50. So from there you can look up. I hope this expression work up to this. Then everything is correct. So what you can see is that now I reference you know the value. The ratio now you also know, right? So you can just take I reference multiplied by this ratio. You should get IC2. Your I reference is given. So I reference you substitute inside, you get IC2. Okay? Which is this ratio time. I reference give you this 1, 2, 4. So IC3, IC4 the same way of looking. You just take the equation for IC3, substitute inside, you cancel away this part, so you get exactly same expression with the numerator change only. Okay, so the denominator is still 2.418. The numerator change because of BC different, area different. So once you get this ratio multiplied by I reference, you get the correct current, IC3. Okay, my I out 3 means this one, means IC3, IC4. Okay, so you can see you can also look up IC4. Okay, so once you can get the collector current, can you get the AC resistance of this constant current source? If you look into here again, you replace it by small signal model, you basically see the R only. Correct? So the small R for BJT, the formula given to you is BCE plus BA over IC. So you can substitute inside accordingly. Once you know your IC, BCE you also know. So for this branch, you calculate IC rate. You know the BCE, so you can work out the output resistor. Can you see that? So I think it's tedious to calculate because of the few this factor coming, and added onto this difficulty is the base current. So I want to highlight from this calculation and show you something slightly different from previously. Let's assume if BA is infinity, what will happen? This is going on, right? If this turns wrong, then let's also assume, okay, the beta is infinity. That means there's no base current. Then you can see that this will be very similar to just now. The MOSFET and this current ratio will be determined by this emitter area ratio. So if that's the case, then this will be similar to the ideal case I tell you is 2.5 times this reference current for this case. So reference current is 100, right? So 2.5 times will be 250. So you get IC2 quite far away from that. Okay. So then the other one is this one is IC3 is 500 times over this guy, but then is only 230, and this guy's over 1000. So you quite deviate quite a lot from that. The deviation mainly caused by a few factors. One is IB. This one contribute a lot. Second one is of course non-ideal. Your BA wasn't very big, okay, only 50. Okay, so then this difference can cause quite a fair bit of difference. So I also have a feeling here we are calculating based on 2 rather than based on 1. So theoretically based on 2, then maybe this is closer to what it is. 500, 512. But check it out whether this value you calculated is 24.14. If 2.14 is based on 2, that means I'm assuming this guy is 2A, not A. Okay? That's the only thing I need to check it out. This is solution for what is more important is the procedure to calculate. Okay, and also the implication. So you can see from the output resistance also you can see which one is better actually, the one larger, the larger the better. And this guy more constant compared to this one with respect to the change in the voltage across the current source. Okay, so can I clear this? I mean, for current source, this one is the most tedious in calculation. Okay. Because we also take into account the beta variation. As that variation will be BCE. So now we come to the third one. This one can help you understand a little bit better. Okay, we are going to look at 2 different current sources here. First, I'm going to look at this guy. You notice that here is ground, and then here is minus VDE, and then this is the diode connection. This is the VDT, and this is also ground. So this is the constant current you want to get. So this is Q1, this is Q2. Okay, so I want to highlight to you in this case there's some assumptions. The whole idea here, R is 43K. So this guy is 43K. This one is minus 5 volt, G is 5 volt. So, there are 2 cases, One is 5 volt, one is 7.5 volt. So, you're asking, okay, VDE, when it is this, what is this IO? When it is this, what is this IO? That's what the question asks. Okay? So, the question I want you to assume that this voltage is 0.7, when it conduct. Because this is diode connected, means you will definitely conduct if this voltage is higher than VDE by more than 0.7 volt, which is true. Assuming if there's no current flow, this will be 0, this is minus 1, so this is definitely enough to make current flow. So now there will be a current flow, but then the drop will cause this guy to be 0.7 volt, and see these 2 are connected like that, this point will also be 0.7 volt. This is C, this is E, this is base. So the another assumption is base current are negligible and both transistors are identical, there is no early effect. See the statement, very important. Both transistors are identical means their area, emitter area is the same. So I don't need to, even if I break it into IC equal to, okay, I can put area, emitter area, then IS, exponential, VDE over VT, then 1 plus VCE VA. So if you assume no early effect, basically means what you say, this guy is infinity. So if that's the case, this term is equal to 0, right? So then this second thing is that now you have this IS exponential VDE VT, right? So is this 2 transistors Q1 and Q2 the VDE the same? B connect to B, E connect to E, so they should be the same. So in other words, this guy is the same, this guy is the same. So the 2 transistors are exactly the same. What does it mean? It's the same, right? So should this current same as this? This is IC, right?
No,
IC2, this is IC1, right?
Bye-bye.
So they the same?
Yes,
huh? So then the next thing is, this guy and this current, theoretically not the same one because there's base current, right? But the question says ignore the base current, right? Ignore means no base current. So in this case, isn't your IC1 same as this IR? Can you calculate IR? If this is V minus VE, yeah? So what is the voltage at this point? Minus VEE plus 0.7 volt, right? Correct? Then what is this current IR? Equal to 0 minus this voltage, right? 0 minus this voltage. What is this voltage? This voltage and this voltage is the same, right? So minus VEE plus 0.7, huh? Divide by this resistance value, right? 4.3K, right? 43K or 4.3K? 43, okay, so sorry, 43K. Okay? So minus become positive. I have VEE plus minus 0.7 divided by 43K, huh? My VE is 5 or 7, right? Two different cases. Then I can look up what is the two different cases for IR, right? Correct? So, if I know IR means I know IC1, right? And then this one mirror this exactly because everything the same, right? The two IC must be the same. So, this will equal to my IR, huh? Right? So then what the question asks you to do is to calculate, substitute 5 volt inside there, see what is the IR. Substitute 7.5 volt inside here, see what is the IR. That's all. Got it? Okay. So this question comparatively faster to calculate. Concept is clear. Basically still based on this, but ignore this means this guy gone. These two match with exactly the same emitter area, same BBE because of connection. They have the same. So in other words, this collector current same as this collector current. And then I know this collector current if I can compute this current because I'm assuming the question asks you assume IB equals 0. Okay, so that's how we do this. I'm going to show you the solution for part A. Okay, so let's look at two cases, huh? The one actually the here is actually the same as what I write. Okay, so now for the first case, minus BB is minus 5 volt means BB is 5 volt. I substitute inside here. So you substitute Y inside here, my I out current, okay, will be equal to 100 micro. Huh? That means this current is 100 micro. If I substitute 7.5. I got the I out here equal to 150 micro ampere. Okay? So you know what is the implication of this question? Calculation is easy, okay, once you get it, but what is the implication? Didn't you tell me this guy is a constant current source? Now my output voltage I change by how much? From 5 volt. Here 0 minus 5 is actually 5 volt, right? The difference here. And the other case, the difference here is 7.5, right? So I increase by 50%, from 5 to 7.5. And then my current also increased by 50%. So it becomes a linear relation with my terminal voltage. This is not really very good as a constant current source. Okay? So that's the reason why if you simply use a resistor to bias this, it's not as good. Because the resistor is because this current mirror this. It's not the mirror no good. It's this guy no good because this guy changed with the voltage across. Linearly. That's why you also affect it linearly. Because this is same as this. So if this guy changed linearly, this guy changed linearly, this guy changed linearly. So it's not that it didn't follow, it followed, but then this is not good. That's the reason why we say if you want to design good current mirror, constant current source is important. That's why you always put the I reference, right? And then put the reason for we not taught this because I reference need a very special design for band gap circuit. So we didn't cover this, so we just put one. Otherwise you say chicken and egg. You design constant cursor, use another constant cursor. No, the fact is we do, but then that because it's a precise one, it's complicated. So I only want to design one copy and then a copy of any of them. That's all I did. Current mirror. Is that okay? Clear with that? And this show you why no good luck. Have to use special circuit to provide the constant current here. Then you can mirror. I hope you see the point. So that is the implication. Sometimes I think the implication is more good in terms of understanding topics than just knowing how to calculate. With calculation, I think this one wants to know the concept. Okay, so the next thing is, since I said this no good, then let's look at how about trying to do another way of current, which is this guy here. I try to use active element to replace this part. Otherwise, can I take this away? I'm going to show you. Actually, it's trying to do very similar thing as this. Instead of doing that, I try to use MOSFET. Again, I have a simple current mirror. Still a simple current mirror. MOSFET. Here is also minus PSS. Okay, I will need minus PSS to question give how much? Again, 5 and minus. So this guy can be minus 5 volt or minus 7.5 volt, same as this case here. So as far as this part, it looks similar. It just replace BJT and MOSFET. So since I said this guy no good, linear change, then this guy linear change, this guy linear change, right? So how about if I use an active one? I try to do this. Use NMOS, okay, then another PMOS. This is DDD, yeah? And then connect here, connect here. So this is a connection. So the VDD given to you is 0 volt. Okay, 0 volt means same as just now the case, huh? This is 0. I just replace this resistor by this. Can you see that? All okay? So all okay, I also tell you that all the transistors here, PMOS and MOS, they have the same VT for PMOS, the actually of VT is same as this guy. DTP is same as this guy, huh? The threshold voltage. Let me put it this way. VTP equal to VTN. VTN anyway is always positive, so I put this. This guy negative, but the magnitude is same as this because I think the question raised it. VTN equal to minus VTP equal 1, right? Which means VTP is 1, minus 1 VTN is 1. Okay, so that means the magnitude of this is the same. Then second thing you need to know is your Kn equal to Kp. The third assumption you make is lambda equal to 0. Okay, so I'm going to take this away because I already showed you. Basically, I'm changing this to MOS. PMOS, I'm changing this resistor to a special this one and trying to see what is the effect. Will it do better? Just now the case for the reference or not. Okay? So let's look at this. You realize your ID equal to Kn over 2 VGN minus VGS minus VGN square. Then my right is 1 plus lambda VGS, right? But this guy equal to 0 means this term I can carry out. So same for the case for PMOS. I will have Kp over 2, then absolute VGS minus absolute VTP.
我会错，这个 first
Okay,
bus
right? Agree?
first bus timing.
Okay, so what I want to highlight to you is that is there any heat current here? Is there any heat current here? No, right? Zero, zero here, right? So this is also zero, right? So which means this is drain, huh? Let me label the transistor accordingly. This is M4. This is M3. This is M1. M2, huh? So I'm trying to say that this is ID4, right? Because this is PMOS, this is drain. This is ID3, right? Are they the same? Same, huh? Because there's no current here. Then of course, this is the IS source current of the transistor is same as drain current, right? So this guy will also be IG, huh? 3, okay? Then again, this guy no current, right? And this is ID1, right? So isn't all the current through every transistor here the same? So let me call it ID, huh? Let me quickly get your understanding first, huh? Because of no gate current, this is the same transistor, source and drain is the same current, huh? Then because no gate current, then this make this the same, right? Then source and drain same current, right? And then no gate current, this and this the same, right? The whole branch one current. Let me call it ID. So whether it's PMOS and MOS, this is the same, huh? For this branch. So far so good. Then question give you Kn equal Kp, right? Whether C1 and MOS is still on the same, huh? Second thing is, let's look at the VGS. I don't know the VGS. This is VGS. This is the magnitude of VGS, huh? This is the VGS, huh? For all these transistors. But then the question says VTP equal to minus VTM, right? Which means these two are the same, right? So now if you compare this equation, if D is the same, ID is the same, Kn, Kp is the same, D is the same, will the VGS the same for all of them? Have to be the same, right? So if that is the same, then this is connected, that VGS is here, right? So here and here the voltage is the same. From here to here, what is this voltage? This is voltage. And this is G, this is S, right? So this is absolute VGS, huh? So this way, this is your same as your absolute VGS, huh? Let me call it VGS, since the VGS all the same, huh? The magnitude. So then this guy, because this point and this point connected the same, huh? So this voltage and this voltage are the same? Yes or no? This point and this point is the same. This point I take it as a common point. This and this isn't it the same? Same. Here to here is VGS, right? Get here source here. So isn't it here is another VGS? I take the magnitude since I put, although this guy is positive, huh? Okay? So let's look at this case here. This voltage here. Isn't it same as this voltage? Here is G, here is S. You want the diode connection again, huh? So this is another VGS, huh? Do you know what is the voltage from here to here? It's 0 minus away negative VSS, right? So the total voltage from here to here is 0 minus away minus VSS, huh? So it's equal to VSS, huh? Alright? So can you tell me what is VGS? 3 times equal to this, right? So each VGS magnitude is equal to VSS over 3. Got it? Okay, once you calculate, you know this, huh? By substitute y inside, substitute 75, you got this, huh? Once you got this, can you get this current? Because this current again, same equation, huh? This is NMOS. The VGS now I know, huh? Because G connect to G, S connect to S, so you follow this VGS, huh? Okay, so if I can calculate, I substitute inside. This part again gone, huh? So VTN is equal to this 1, huh? Km, question also given to you, yeah? Okay, so substitute inside, you'll get your answer. Okay, so I am going to show
The
you
next chapter.
how it was done, okay?
Yeah, okay.
So now let's
Zero
look at
also.
this case. So the key point is,
I got extra couple.
same as just now what I told you, all the current through this branch is the same, for the reason I mentioned.
Frequency.
And then since they are the same,
Quite fun.
then because of diode connection, this and this is the same, this is one BGS.
Because my
This and this the same, this another BGS, this and this is the same, another BGS. So there are three BGS across VDD to VSS. So I take VDD minus VSS divided by 3, I get this BGS. Okay, and VDD is equal to 0, VSS there are two values. So for the two cases, I can actually get my VGS. So for the case this is 5, my VGS is 1.667. Then I substitute into this equation. Kn is given to me. VGS I substitute inside. VGN is given to me. I substitute inside. I can work out that the drain current here is 89 microamperes. Okay, okay. So now, if I change my VSS to 7.5, then I put 7.5 here divided by 3. So I get each VGS is 2.5. Then I substitute 2.5, I put Kn here, VTN here, I work out the current is 450 microampere. Got it? So this one, calculation wise, I will tell you, the key point is understanding why all the current here is the same, because there's no gate current in each of the transistors. And drain and source current is the same. Once you understand this, the next thing is that understand this because of diode connection, VGS and VGS is the same for the transistor. This guy is also diode connection, gate connect to drain. So the gate source will be same as drain source, same for this one. So then I have 3 VGS across here. I can work out individual VGS. One that is done, this is same VGS, so you can substitute the VGS inside and can work out the current. So as far as working is concerned, not that bad for this question, but again I like to tell you the implication. Implication here is actually if you notice this guy compared with the simple current mirror using BJT just now, I'm just changing the BJT to MOSFET, and also I change the resistor to this guy. So when I use the resistor, I say no good because actually you do a proper mirroring because everything I reviewed. But the problem is why this guy changed is because this one resistor is linearly related to the voltage across it. So if the voltage across it changed linearly, so this guy also changed linearly. So now look at this case. Actually it's worse. Notice here, across here the terminal voltage is 5 volt. Across. 0 minus 5 is 5 volt. The second case is 7.5. So if it's a good constant current source, I would expect that the voltage change by say 50%, the current should be changed much less than that. But in this case, it's not, it's actually quite worse. Changed a lot. And why this is quite worse? Does it mean this simple current mirror doesn't work? It's not. If you look at this, then these two currents are exactly the same. It's mirror. But what no good is because this current here, the drain current is dependent, or this side is dependent on the voltage there, and this time the dependent becomes quadratic because of this equation. Square. That's why it becomes worse. Okay, because your VGS now is dependent on so much here, right? It's about linear, but then you are linear, but then you square it, you make it worse. The current deviation is now worse than previous case, the linear case is squared. So as a result, when this guy is no good, it changed with this guy, when the mirror over it also changed. It doesn't help very much. Got it? Okay, so again I always say, this guy is not an easy one. You need to make this guy very constant. Doesn't change with this. Then you can mirror it over. Okay? So that is the key point for this I clear this?
Press now, bro. Okay, now stand me for sure.
Okay, I use this to bring in the wheeler current mirror concept for you. I take the question here, and then I explain a bit about wheeler current mirror. And then I also want to take this to tell you previously, I think I told you before, this guy, this wheeler current mirror, only after this person who do this is actually quite interesting circuit that it can be used for the thermometer because of the proportional to absolute temperature voltage. Okay, so PT, AT, yeah. So let's look at the circuit here.
He want to see you like, oh, he's trying to you scope the shit out. You know, 1 minute here, yeah. Huh? No, go.
Okay, before I pass this circuit, let me do the basic wheeler current mirror first. I think now you should know, assuming if I can do this guy a constant reference to provide some constant current here, assuming this IC, if you know this, it's approximately equal to this guy, right? Okay?